Hello, 5:38, Sunday, June 18th, 2023. Well, I imagine I might try the advantage this way today of this recording and see how it goes to record a little bit more about the talks about the differential descriptive dynamics or the descriptive differential dynamics. What with regards to the usual study of analysis and the schools of the dynamical systems and the dynamical modeling, what result a usual course in fundamentals that result for our elementary approaches to analysis, what make for arithmetic and algebra and number theory and geometry and topology and analysis, that up above set theory or part theory, what results some kind of fundamental approaches and the aspects of the foundations as it is, or as it were, from a fundamental theory with only one relation, or L, or and its complement membership, or how otherwise that becomes an axiomatic then descriptive theory, whereas a model theory is what's so the meta theory that implements making for the relations of a proof theory or model theory, those being equivalent, the same thing. That the idea is to get back into some more of this discussion of the description of the complex numbers, which is part of the development of some tools or some diagrams or some models of elements that fit within the realm of analysis to complement what are the usual elements of the arithmetic, the algebra, the geometry, largely, topology and function theory. Function theory is not to be left out. So that for the complex numbers, what can so arise is the example of a higher order organization. Here is framed in terms of something after what's being called the identity dimension. So what's this identity dimension? Well, the identity dimension is approximately the same thing as considering a straight line with slope 1 equal to being that dimension. And so in this manner, what would otherwise be the x and y axis, which so frame it, or any number of axes like x, y, z, or however you so care to describe, in a Cartesian coordinate setting with an orthonormal vector basis of a vector space. Something like only the positive numbers in each one of those, the first quadrant in the usual xy plane, the diagram of r squared, of the Euclidean space assigned a coordinate origin and called r squared, or Cartesian space. Then the idea is that to arrive at what would be called this identity dimension is only to consider that first quadrant, and then x equals y is the function. And by doing so, what's afforded is that then that becomes what would be the functions would be defined in terms of it. And so a value on that is basically then as to whether the units of that are the same as the integer lattice points, or whether they're the same as length 1 in the semi-dimensions, which now x and y are cast to be, or otherwise about how it works out that something along the lines of that coordinate space, that the treatment of that setting as the coordinate setting, makes it so possible. Then what's so arrived at is that then various framings of otherwise functions in what would be the octants, or the upper and lower half above and below that, are symmetrical about that in terms of x and y. And why that ends up being kind of a place for that is what it does is it express a relation that otherwise is the orthogonality or the asymptote of a singularity, into instead what results that that's only 45 degrees, or pi quarter radians is theta, the angle in polar coordinates of those, with respect to that coordinate setting in that transform, so that functions and formulas can be graphed and charted in that, and according to that they're symmetrical about it. At the same time, that can be projected back to where those become orthogonal, and then that they become obtuse and become the straight line. And so essentially what can be represented in that one quadrant can then also be used to reflect on the semi-plane. And so in this manner, one thing that ends up being resulting is that the formulas where otherwise our usual singularities are 0, there's no division by 0, and that 0 is a closing division to all its elements, including 0. And then there's I, for example, has been talked about. The square root of -1 is an example of closing root for negative numbers, or root of -1. There's been quite a long discussion here about the roots of unity and complex analysis, and the roots of -1 and this kind of thing. And then it so follows that something like the original and singular analysis about the roots of unity also then gets into roots of 0, which would be about the infinitary. In this non-standard setting, whatever is the non-standard is whatever is the infinitary. Non-standard implies anything that's infinitary, like the non-Archimedean in a field. But also here there's a usual stronger sense applied that the non-standard is the non-standard infinitary-regular. What does infinitary-regular mean? Well, what infinitary-regular means is that basically that it's an effective infinity that's a fixed point, and it's compact as of the compactness of the natural numbers of point at infinity. And so instead of, for example, defining usually arithmetic and defining the numbers as starting 0, 1, 2 and carrying on outward to infinity, it's that they start between 0 and infinity, and then it's just filled in the middle. And so what ends up becoming regular about that, or rulal, is there's basically more than one definition of continuity. Now, the definition of continuity that everybody's familiar with first, of course, formally, is the delta epsilonics definition. It so follows and arises from the usual course after precalculus, where it's determined that the infinitesimals, you know, from Zeno's paradoxes and the resolutions of motion, and the notion of a constant uniform difference that's infinitesimal in numbers that comprises an infinitude of iota values exactly equals 0, 1, and a sort of infinitary regularity that does not exist for this course. We're instead going to use delta epsilonics in the definition of limit. So what we're going to end up having is that we'll have a notion of an infinite series, and then that in the course of that series we'll be able to approximate as what's via methods of exhaustion, which is the ancient term, as it were, or where it's possible in a geometrical setting to start with infinitely many operations and to go to the limit, to fill it out, to exhaust. All that what remains is in terms of the limits and how things arise in the infinitary and how they're not so in the finite. That then the idea that what this will convey is that the line continuity is somewhat more primitive than that, and is actually just a function of the integers, including perhaps or not, but still just defined as not just a limit of a value as a free parameter. It goes to infinity, but a limit is of a function, that the simplest kind of function, n over d, n for numerator, d for denominator, and integers, has that the limit itself of a function is what ends up being defined and described and derived. Line continuity. So for line continuity, and then this field continuity, which is standard, and which ends up establishing a similar kind of thing about the intermediate value theorem, which makes for two lines crossing, and when they do, that they cross at one point, and the mean value theorem, but otherwise then the fundamental theorems of the derivative and the fundamental theorems of the integral calculus, or the fundamental theorem of differentiation, the fundamental theorem of integration, that after what set theory makes for a model of real numbers as the equivalence classes of sequences that have the Cauchy property, that they have a limit, and they converge to a limit, this series, has that then there's axiomatized that after the complete ordered field, that this class of these sequences that are Cauchy have a closure, Dedekind completeness, and then also that they have a measure, so they have axiomatized the least upper bounds property. It wouldn't otherwise exist via inductive inference, although it does sort of as via deductive inference from having a continuous domain already. They're so axiomatized to exist, and then there's measure 1.0, which so axiomatized exists. And then as we've been talking about in Lebesgue integration, Lebesgue measure, that that sort of measure theory is what's so attached to these standard field reals, field continuity, and the objects of the field continuity, the continuous domain that is the complete ordered field. So for line continuity also has this least upper bound property. It's very trivial. It's just next, and And then it has the measure property. There's a variety of ways to make a length assignment, basically corresponding to that it has a sigma algebra and makes for measure all the definitions according to what holds up an intermediate value theorem first, for such as like Newton's and Leibniz's calculus or Riemann's, and then for Lebesque's as well with measure theory and what, which is pretty much modern and standard. Then the other notion in terms of a continuous domain, which had been defined here, is something along the lines of Lebesque measure, then field reals. Oh, and then for the signal continuity, where this notion of the signal continuity is that one can consider a line segment that's everywhere discontinuous. There are points everywhere, but there's everywhere also a gap in any neighborhood, however arbitrarily small. And so what this makes for is a sort of domain that is making for a signal continuity, because basically doubling that, or its complement, plugs that together and makes for a halving space, which makes for a signal continuity, or a third kind of completeness, or continuous domain. So for when people think of Dedekind completeness, and for the field, complete order field, and they call that gaplessness, and they call that completeness for continuity's sake. And then there's basically here, there's line continuity, and it has line completeness, and there's field continuity, and has field completeness, and there's signal continuity, and has signal completeness. And these correspond perhaps most accurately with something like regularity, as we were talking about. What's this infinitary-regular, non-standard? First, for the line continuity, that its extent is always between 0 and 1, and then that it just divides infinitely in the middle what those are. And then similarly for the field continuity, it's about the ordered field and its members, and then with regards to that, then it's often related in terms of the coordinate and that kind of setting. And finally, for something like the signal continuity, that the signal continuity essentially has what you'd call, what's the word? Completeness, for this infinitary, non-standard, really irregular. It's kind of an extension of the perfect reconstruction, or the sampling reconstruction of Nyquist and Shannon. This is the usual sort of theorem that for any kind of periodic function that's, say, in the digital, if it has a given frequency, then if you have another frequency and can supersample it at twice that frequency, then what results is that you can then write out what would be terms that would make for reconstructing perfectly the original signal. And then it also reflects in things like the rationals are huge, and otherwise that though they're, the cardinals are the same, and that they're considered, according to standard measure theory, measure 0, the rationals, or any other sets that's nowhere continuous but dense and equidistributed in the reals or continuous domain as a prototype, that they still instead have this notion for the Dirichlet function and this or that or what, that they do have analytical character and do end up being measurable, and in this non-standard sense have non-standard values. Then these three different realms of real numbers are basically treated separately, and then they connect together eventually only at the integers, say. And the lattice points to the integers. That for numbers, one way to define them is the complete ordered field, and as some equivalence class of any member of which has a sequence as a series that has the property that is after Cauchy, who is a mathematician who described the property of the limit and convergence and some of the first tests for convergence and this kind of thing. What so arrives at that for a simpler milieu, it's just the integer part and the real non-integer part between 0 and 1, which also defines a real number. So in this sense, then, this line continuity only exists between 0 and 1, and so for a larger setting, between, for example, all the positive numbers, you associate it with also an integer part separately, and then this non-integer part. Then the signal continuity, and as with regards to whether it's also only exists for some bounded region, probably is kind of as like so. And this gets into why for our overall meta theory and our model theory and how it's all going to relate to any theory that's utterly fundamental in the logical objects and any kind of non-logical objects. That what kind of arises is that the, how you'd say, uncountability is a thing that exists in a particular subtheory of one of these set theories, one where it's axiomatized away that an infinity or a set containing infinitely many elements wouldn't contain itself. And then after that, with the power set result, then we have all of your Cantor's kind of results stood up about uncountability. And so it kind of has to be worked out that whereas this notion of the line continuity or Aristotle's continuity is ancient and it's been around forever and it's very intuitive for everybody, and in pre-calculus we talk it away. And then the signal continuity is kind of a higher level notion of continuity, and it kind of rises later in a sense of analysis in the signal. And that the field continuity is our most standard milieu for formalization and for the efforts that have gone into making for a foundation and a formalization, that at least we have one way to talk about that a series of functions has real analytical character and that it shares a common derivation and definition. So all this kind of thing has been largely underexplored by what we call standard, because first of all, it involves considerations of the function theory deep within the axiomatic set theory and the descriptive set theory to make it so possible that what you can arrive at for having line continuity is as well not inconsistent with it being a countable domain, and similarly so for the signal continuity, and as about for basically a roundabout way to talk about the space of all real functions in the long line continuity of Dubois-Reymond, who illustrates another aspect of completeness. That then for this Aristotle line reals and Dedekind field reals and Nyquist-Shannon signal reals and this Dubois-Reymond long line reals. Those are four definitions of completenesses or completions, make altogether a replete setting. And then that each of the ways that gets into the existence of various functions, it has that there's a non-Cartesian function, this line continuity. It's only set up as tenuous or attenuating between its endpoints. In this manner, it exists while not being contradicted, and thus it results for axiomatic and descriptive set theory that it's a thing. So these are the kinds of things that have helped establish that there's at all in non-standard setting. And then another notion that's been considered here, then carrying on, is that there's along the lines of the singularity theory is a multiplicity theory, because any singularity is to be explored as a geometrical object in higher order spaces and higher order surfaces that has two branches, that is only a line or a dot in smaller dimensions, less dimensions. How that works is for something like 0, that if you were to divide by 0, then it would be an infinity. Okay, and so it's left out. And at the same time, if it were to exist, then there'd be all kinds of considerations whether that's a fixed point or how that exists or what goes on with that with regards to infinity. Now, similarly with -1 and its root, square root, as it's an even function, square and square root, then it would not exist, because there's no product of two negative quantities that is not a positive quantity, non-negative quantity. And so what is deemed to exist is defined to exist is a complex root of -1, and it's called imaginary, and it's called this imaginary quantity. So what was done here was talk about the singularities about systems of equations. And in algebra, you can define ratios of functions as functions. You basically, any expression in variables is a function. About whether then they're sensible, fungible, and tractable. So the idea of these singularities is that this notion that the identity dimension fits in place for a lot of what become these differential equations, because kind of the idea is to figure out a pretty good setting of the descriptive differential dynamics. What are all the kinds of differential equations? What are all the methods of analysis, figuring any aspect of mensuration, measuring an area, or differentiation, finding an instantaneous point or rate of change on any of these surfaces, any of these points, in any of these directions, should have a kind of an overall surrounding context, and that the dynamics of its definition and its description are well defined so that different subfields don't conflict each other, and it doesn't end up that they can't really sit together, for that their terms would be incompatible. And so that's the idea of figuring out when the field is going in various different directions to make different things tractable, that it's still necessary that then for each of them that they need to keep at least some level of common definition, and where it's necessary to disambiguate definition, that's readily accomplished without much else being, how you'd say, lost in the translation, in the interpretability and the equi-interpretability of these different subfields of these same objects or different objects. And so these are the kinds of things that have been going on in just in the course of talking about the symmetries, submersions, and sheaves. That symmetries are all about methods up above and about the geometrically that kind of get into things that would otherwise not be accessible to just algebra of the functions, because they reflect things in the space or after transforms in the space or in the settings and the coordinates and this and that. And things like these Lie algebras and these other things, and the complex analysis and the hypercomplex analysis is much like that. Then there's also like the notions of submersions and immersions from this differential geometry. Is kind of like, well, we already have it, so we're not going to have division by zero. It kind of goes the other approach to the non-standard. It says, let's restrict it more, and then we'll be able to make much more tractable and sensible as long as they all face exactly to the left, 25 degrees. That being just arbitrary, or just to point out that it's in a sense arbitrary, when the idea is that we're going to deal only with functions that have not just a non-zero, not just have a non-infinite slope, but also have a non-zero tangent. And so the idea would be that the function is non-zero and that its derivative is non-infinite. In this kind of manner, making for that there's two singular points left out. And so that gives them some more methods that end up becoming fungible and tractable, that differential geometry, or at least from what I've read about it so far in submersions and sheaves, kind of has that as its precept. Now, that is not necessarily compatible later in definition with the wider definition of function, where functions over time have had much of the most dynamics in what they entail. Since, for example, they're only real functions, to then they're only discrete functions, to that they're nowhere discontinuous functions, to that they're piecewise, there are gaps, there's classical functions, there's smooth functions, there's anything you can draw with a pencil and paper, anything that can be represented in a space as of the Cartesian. And there's these, then later, everything basically sits in a Cartesian setting, and then whether or not it's Cartesian and that its Cartesian product exists or it's non-Cartesian. And so then there's also, then with regards to that, when there are regular functions and they're one-to-one between the domain and range. Whether we get into the reasons why we talk about defining functions in terms of the domain and codomain, the range or an image, or the image and range, or the domain and range, that the domain and range are the usual preferred definitions for the left and right for f, and its inverse or reciprocal often g, or f to the negative 1. Or that otherwise when we compose functions f with another function to make a substitution or compose a different function, f and g. F and g are the usual names for any given functions. And then there's this idea that the functions that so exist are according to what matches the definition. And so in a lot of these different subfields, there are basically functions that do or don't exist. And then those that do or don't then are related by what's called operator calculus on them. And this is where the notion is if the set theory is way down below, and then the idea is to figure out this operator calculus way up above it. And usually that's where you attach something like type theory and category theory way up above, besides, of course, that there's type theory and category way down below in the foundations, with the usual kinds of ideas that you end up wanting to make things simple in diagrams so that the high-level apparatus and constructs can kind of be written in squiggles, and connected together with that, then you still have some confidence that those elementary aspects that are built as up of a higher level are not invalidated or poorly defined or not well defined as they're carried on down below. So getting into this identity dimension, then the idea of this identity dimension is that after 0 and I, or the root of -1, then the idea of what's to result is this identity dimension makes it so that it's just like y equals 0 in terms of these functions that are symmetrical about the domain and range. Now, there are not so many functions that are symmetrical about the domain and range, but all the circles are, for example. And then you can imagine anything that's symmetrical about x and y is kind of like so. And so anything that doesn't cross x equals y and lives in the octet has an image of, as about it that makes it so that it's symmetrical about it. And then anything that's otherwise having any kind of contrivance that makes it so that by transformation of coordinates that you can replace x and y. It's kind of like so. And then there's also this whole notion of for these trajectories and orbits, that then for each of these orbits there's these trajectories and that they have these fields as they cross, so that anywhere you can describe a set of level lines or plane curves in the quadrant, then, and those define integral equations, just like they're solutions of differential equations, which has been much of the talk of what we had here. Then also you can reflect those as having this character or this property that the identity dimension is singular in it. That it's just like for y equals 0, and anything that would have to do with dividing by 0 would be kind of like so in it. And so this is a way to make a diagram, and the idea then, if that's a restriction in terms to some sets of functions and formulas that only exist in this manner, then it's still possible to describe for them all kinds of methods of symmetries and submersions and sheaves in the differential geometry, and to make it kind of tractable for a couple different things to approach what it can be for those that become the singular solutions in their envelopes. And where the envelopes make for Mariology, which is kind of a way to try and avoid these locks in the or what would be the orthogonal, like the gimbal lock, or otherwise the singular, the asymptotic, that Mariology and the meromorphic and makes for this kind of approaches then, and also for making systems of integral equations and their solutions what can be arrived at quite directly, or making for the inference of the existence and uniqueness of their solutions, or especially their existence of what are otherwise the existence of uniqueness of solutions, counterexamples to the existence, thus the existence of non-standard solutions. That's really kind of my interest to find these things, because otherwise this field is very well explored, and it's the bread and butter of all kinds of mathematicians because it's the field of analysis. And when you get to a lot of these, basically where the sidewalk ends or where the fence is around the field, and the existence result is that this side of the fence exists, and the uniqueness result is there's no other side, then the idea is that when the actual real non-standard analysis exists and is well-founded and well-defined and can be made rigorous and formal, then what results is that it also adjusts or makes room for counterexamples to what would otherwise be the uniqueness results now only become kind of distinctness results. In otherwise, that the world is functions, and the objects and the relations between them are functions in a function theory. Any relations are mathematical objects and are mathematical objects and are mathematical objects, ... That this is the kind of thing that allows for a pretty usual general setting of what is the mathematics with the goal of enriching it and equipping mathematics with actual non-standard methods of analysis with real character, because it's a real character that only ends up being valuable and relevant. The qualitative is relevant and can be something to be ascribed as descriptive, but here that the qualitative ends up being real valued, and that basically in terms of integers and their integer part and non-integer part real numbers, and in terms of the magnitudes of numbers, and corresponding all the rest of the relations in terms of the field of numbers. So, studying a second course in differential dynamics after basically the first course of a couple years of calculus courses in school, and a couple years of calculus courses in getting a mathematics degree, and then some learnings about there are various applications kind of in dynamical settings or dynamical modeling, that being basically to frame any kind of these matters of problems that eventually involve calculus in terms of those. Here, this second course is to kind of try to approach the field in its historical setting, where the idea is that its historical setting has reached a mature state about 120 years ago, and in terms of its definitions that were the working definitions of that time. And then it kind of metamorphosed about 60 or so years ago, or 40 or so years ago, into a bit more geared towards ending up at a stopping off point for numerical methods and computational analysis. That the idea is then that for the differential setting up above analysis, in real analysis, the idea is to approach it as a field altogether, to make it so for this descriptive differential dynamics, that the dynamics and the definitions are sorted and squared, and the dynamics in analysis and their definitions and derivations are sorted and squared. In programming theory, we kind of talk about starting with declarations, and that's basically the shape of a function. It's a parameter list and its name and a signature. And then it's the function bodies as implemented are the definitions. Now, in mathematics, it's much more about that there's some definitions, and then there's derivations. The signature of things of sorts is kind of their definitions and their derivations. This is just a sort of example in descriptive dynamics, in the definition, descriptive definitional dynamics, where there's two fields with the same sorts of objects that then, if it's clarified how their names sit together, where it's like they say in the software engineering and computer programming, that it's all about naming things, so it makes sense what they are and what they do by their names in their reading. And when one must read through all the source code and understand and follow the trail, it's similar in the same, and so for derivations after definitions in mathematics. So as far as that goes, because it takes a lot of work and time to discover and find methods and make sensible, fungible, and tractable these methods in mathematics, a lot of work has gone into that, and then make that formless and make that rigorous. And then how that works is that we call that a foundations, or we call that a axiomatics. And it's familiar from geometry is Euclid's axioms. And with those, oftentimes in geometry we're shown it's like, hey, here's form and proportion and proportionality, and you can find that for any two lines you'll notice that opposite angles have the same angle. And there's some various formulas and theorems that arise very directly just from drawn lines on the page. And then when axiomatics are introduced, those are pretty much cumbersome because it takes a while to determine how to derive from those. What is the methodology to go about showing proofs geometrically, or making geometrical proofs, or illustrating what's so is so from composing these proofs together and making from elements and basic elementary theorems and then fundamental theorems of subfields that establish these closures and completions and otherwise make for results given in the subfields, that then those in their matters of definition become their own elements. And then in terms of how those bridge, or you have the intentionality and extensionality results in the lower level, back to the more fundamental lower level elements, that those exist, that these are the kinds of things that they get into and establishing an approach to axiomatics in deterministic theory, like geometry. And so anyways, these days when mathematics is trying to figure out how to do that writ large, or for the whole, how you'd say, universe of objects, as it were, although it's rather restricted and doesn't include a universe, and there's matters of that it is regular in a particular way. It's called well-foundedness, or the regularity of sets, that their transitive closure does not include itself. That it's still so established, for example, via delta epsilonics later, and axiomatizing Dedekind completeness, and axiomatizing after that Dedekind completeness least upper bound property measure 1.0, the objects of real analysis. That is just another example of how these higher level theorems are built up in this axiomatic theory, and as of the elements to make it so, then the field has its theorems, and those stay valid throughout. That these are the kinds of matters that get into what's called the descriptive set theory. That's descriptive in this manner. That then when it makes for that these descriptions are syntactical, and in the language of the logics of the elements underneath them, and the language of the theories of the objects of the models and the proofs of the theorems underneath them, the models and the models, or the proofs and the theorems, that these are what make it so to say that that description is attached and well-defined and well-behaved and formally guaranteed, and that there's a sufficient level of rigor that makes it so that it's not ambiguous, nor does it break. And that these are sorts of things that then make it possible to say something's proven or proved in the more elementary and axiomatic system. Now, my general notion of a concept of things is then it results and arises from axiomless natural deduction, the very existence of logical elements at all, that they are plainly just framed as a consequence of logical existence of truth. That the very existence of truth makes it possible to axiomatize a universe of a set of truthful mathematical objects, where only one of them is this sentence is not true, the liar paradox, and it only serves throughout the rest of the theory as a prototype of a mistake or a fallacy. Or also in the realm where that entire theory is turned over to alternation and 0, 1, and building out from that a model of change instead of a model of state. These things have to be considered when there's only one theory for everything to go into it. That there are no paradoxes, and then something like axiomatic set theory just arrives by, well, just take the one that's a matter of only one relation relates as elt, and the rest is logical. And then you can restrict a fragment of that for the ZF set theory. And similarly for the axiomless natural geometry, to have some idea of this a continuum. It's neither, it doesn't start really as either a point or a line. It starts as a point in a space, and then the point just grows out of that as a spiral space filling curve, and it builds an infinite dimensional space at the same time as it builds the first line. Or you can just even start much simpler and just say it's just between 0 and 1, draw a line, and that is the fundamental primitive element of this, what would later be an axiomatic space, but is axiomless. So that is a usual course that gets into why, and then that foundations arise from that. And then that is simplified by saying, okay, we're going to name these things and call it axiomatics. And now, furthermore, we're going to take away anybody having to work out how to have a fundamental theory of truth from nothing, and also take away any objections which would arise from saying that, because you could always just argue that that's nothing. And that kind of thing. That axiomatics so arises from it. And so the same sorts of axiomatic theories that really become successful in mathematics are all going to arise from the same things. Mathematics is fundamentally a common language shared by everybody. There is essentially fundamentally no possible way to make something that's mathematical that's not mathematical. It's kind of a definition in terms. And that said, there's lots of definitions of what's mathematical, and in terms of relation and after logic, and then for science and all this kind of stuff. and what's fungible is not necessarily what's mathematical. So there's lots to be said also for just the descriptive and the language of words, and the not necessarily non-mathematical or unmathematical, but just as matters of definition in words, that you can consider that as an axiomatic theory, where otherwise theorems are not applied concretely, but they can still exist. These are kinds of things that get into a theory of everything. So as I started talking about this, what I started talking about was this idea of the differential systems and a study of the differential systems from 1900s and fin de siècle, 1900, and Y2K, year 2000, and how those differ in terms of the ones focus on the elements as plane curves and their integral equations. Those are the differential equations. They're equations defined in terms of their own integrals, or differential equations, vice versa. And vice versa, then the differential equations and their solutions, which are these systems of the level lines or plane curves. So that's just sort of the beginning to make it so that then, well, now at least I can deal with all the results that came before and all the results that came after and figure out how they fit together, besides whether one or the other is lost in either way. Because the old school methods end up leaning towards geometry and about using analytic geometry and algebraic geometry to solve things, whereas the new ones live in a world more of algebra, and especially for places where it ends up that they're linear, so that even in large systems, they can be solved by large computers and vector methods and this and that, or algebraic geometry. That algebraic geometry is kind of a world in the middle, and so we'll consider the tool schools of somebody like Lefschetz and Picard and them as contra to like Bourbaki or whatever, in terms of the one leans towards geometry, as I do, and the other one leans towards algebra and a space of words, as was discussed earlier, in terms of the difference between a usual setting of the space of the points of a geometry or continuous manifolds, and the space of words and definitions. That these are the kinds of things that they would carry on. So I was studying then this fin de siècle approach, and indeed a pretty simple textbook sort of approach from the university catalog of sorts at the time. And then getting into it starts with definitions and numbers, and then it starts with the definitions of equations that result that they are for various particular contrived instances. And one of the first ones introduced was this linear fractional equation. And then for Clairaut and D'Alembert, which end up being for these systems that have some of their solutions end up being just lines. And for example, this identity dimension, which would be a solution, but instead it's part of the envelope, say, or it's part of the singular, or it's otherwise about where it would be like dividing by zero, and so it can exist, but at the same time, it's the same thing as what would be the point in infinity, or that it would be the same thing as zero, otherwise in this space, then it makes for a reason to have it then as in this reduction of the system to only the positive and positive numbers together, to make up for then that these changes in one of the other, these semi-dimensions, make room for the rest of what I need to bring from this replete definitions of continuity for analysis. Now, what does that mean, replete? Well, there's complete, and then there's replete. So the field continuity is complete. It's gapless. And so is line continuity is complete. It's gapless. And signal continuity is complete. It's gapless. But they're three different definitions. But together they combine to make a more replete definition. But they can't just be used interchangeably. They have to be used exchangeably. They have to be used in a manner where the bridge or the ponts between them are defined, so that the bridge results in making for the transfer principle applying in terms of generally the ideas down in the level of the axiomatically elementary objects like sets, or primitive fundamental relations in the ultimately grainy, or in the models that implement these things fundamentally, that they have their natural operations exhibit these differences in the carriage of the terms between numbers from the complete ordered field, numbers that have integer part and non-integer part, those being different, but having the same space of real values to share, and samples that kind of live from the signals, those being an example of just another kind that has to exist in terms of all the theorems that exist above and below and is about and around them. So these are the kinds of things that go into then why this ends up being just kind of a foothold of a sort, or actually just an idea of making an application, because then the idea is to make for a realm by itself of this kind of thing, that it's not so much about these non-standard continuities and such, except when it comes to applying stuff like this doubling space of the line continuity and this halving space of the signal rails. That the line continuity is like a function between the non-negative integers and 0 to 1. 0 goes to 0 and infinity goes to 1, and in between them it ranges in the range from 0 to 1. Now the idea is that it's a discrete function. It's only defined on the integers. Its measure would be 0. It would not have an integral. The idea is that it does have an integral, because it looks like half of a unit triangle if you scale it, half of a unit square, a triangle, if you scale it all the way back down to 0 and 1. If you squeeze it to fit within 0 and 1, its properties of being constant, strictly monotone, increasing, or make it like so. It's an example of a non-standard but rulal, infinitary-regular or infinitesimally-rulal standard character implementation of having an integral. And that the funny part is that from having the points all divided like that, each one, they are two-sided on a line instead of one-sided in a line, that the area doubles, and so it's area 1. And what this means is that the integral of this equivalency function exists in this area equals 1. The doubling space is the idea here, or the halving space being its reciprocal. Because basically, when figuring out how to make something discrete from the continuous, it doubles or halves in one dimension. In higher dimensions, it's related by how many points it takes to point to it. Similarly with the signal continuity. So looking at this identity dimension and its semi-dimensions, x and y, my idea is to attach handles to that to either side of the x and y, to make it possible then to figure out when one side is continuous and the other side is only dense or sparse, or when there accumulates density and it becomes continuous. That the idea is that then for Vitali and Hausdorff, but especially kind of for Vitali, that who established the first kind of function that the mathematics at the time said, well, this has to be non-measurable. Well, what is it? It's taking 0, 1 and splitting it up into parts, and it has to be between 1 and 3, and it's called 2. That's kind of what it is. So it's taking an extension of it like this and making it so that geometrically it's like so, and then that it arises from the very natural properties of this axiomless natural deduction. That's, of course, the goal, that it reduces to the mathematics that would be the same that anybody could arrive at or figure out or think up. And they could, because it's true that these are the kinds of things that it is. Then besides, I was also kind of interested in looking at it because it's a way to make abstract the usual notion of the axis itself in its placement in a coordinate setting. So it's kind of in this notions of the degenerate and the quasi and the pseudo elementary of these objects. It makes it so for this kind of subatomic, in allegory to another realm where it's highly fruitful to make this sort of analysis of what are otherwise these atomic, uncuttable objects, that they're made of parts, or how they are made of parts, where they are made of parts, and this kinds of thing. That such has amused me also in carrying along just my second course in differential analysis, to reach to the point where I could feel that it was a useful handle in a test to apply to a lot of these different things that have come up so far, from the linear fractional equation in Clairaut and D'Alembert, where it fell out, that this can be read from some of these past hours and hours or so of me discursing, in a sense, or just reading and offering my opinion and comment in this context and figuring out these kinds of things. That these are the usual means of entertainment to just stay interested in a subject while carrying along it, while as well trying to figure out a way to give something back to the field. That eventually the goal of mathematics is the applied. And so for many, it's just like, I just want something I can pick up and put down when I'm done, and to get done. I want it to be sensible, fungible, and tractable. And then as long as it's reasonably correct, or in my engineering case, apropos, it's fine. It's satisfactory. But then others, they're interested in the whole foundations, or at least they want a foundation. That's really the point of axiomatic set theory in modern mathematics today. There's at least one fundamental approach to an axiomatic set theory and descriptive set theory that you'll find a coherentist and correspondent adherent to truth will say is so, because empirically it's also so, and pragmatically it's also so true. Then there are foundational fundamentalists who won't accept anything except that which is itself true for its own self. This sort of axiomatic deductive approach, because it can't be stipulated. It has to arise. It's purely logical, totally logical. So that's fundamentally that's the pure mathematics. Mathematics only for its own sake, but really it's for the applied. That there's no such thing as only the applied or only the pure. I mean, either or is one or the other. And then when it's an implementation, you might call that just a model, just like that which carries out the same actions without knowing how it was so made, that kind of thing. But in a higher sense, there's that where all the derivations are justified, compared to those that were just printed out and can be recalled on demand models. So these are the sorts of things that have gone into this kind of approach to a second course in differential analysis. In this case, these symmetries, submersions, and sheaves, where sheaves, of course, are topologies, and they really represent the gathering and the bringing together of realms of these point sets in what are geometries objects, and as they're from Euclid and so on, the points in space and this and that there's only something like points and lines in Euclidean geometry, but in this world of point set topology, that there are points in their spaces and points live in spaces. And then there's that neither can really be the other one. You can't really collect points to make a line. You can't really divide a line to make points. Except in this extreme case, it's broken down in the analysis that this Aristotle's continuum exists, that Zeno's continuum exists, and Zeno's uniform motion exists. And then as to how that is well defined and does not allow ambiguous statements or allow the extension of inference to make mistakes or logical errors or paradoxes, is in terms of these objects and elements as they so define and describe to make possible to derive. Points and spaces, it's a geometry of points and spaces. So carrying on from that, then how this has been arrived at with then topology has that there's various kinds of topologies. So just like each of these continuities has their own thing that makes it so that they're complete, although it's the least upper bound property largely, and it's measure 1.0, makes them gapless. And then there's also that they each have different topologies that would kind of make them so. And so then a lot of results that end up being about a topology either have to be figured out whether they're derived in terms of, for example, that they're members of an open topology or they're members of some kind of anti-open topology, or otherwise whether the sheaves are exchangeable, they're interchangeable in the descriptive dynamics of the derivations. Descriptive derivational dynamics. These being kind of approaches to an approach to mathematics. You have the descriptive and the derivative for the derivational for the differential in the dynamics. When things are simple and linear and they can just be closed, when they're not, and when they make their outer products that each exist on their own. And the independence and dependence of variables and derivations and such things that follow from logic. That logic is our guide. Logic is our rule. Well, I hope you've enjoyed this today. It's a little bit different topic, and of course, I haven't really gotten any reading done yet. Let's take a look here at reading. What's this thing? So here's this book. This book deals with complex variable theory and its applications. So we're talking about the Jordan curve. The Jordan curve theorem states that a simple closed Jordan curve divides a plane into two open domains which have the curve as common boundary. So we talked about the interior and the exterior and the very definition of the Jordan curve. And these days it's called something else because it's called just a simple closed connected curve. And this is one thing where sometimes objects in mathematics are named for the people who discovered them, because it'll be associated with their other parts of their bodies of work and also the other parts of the other people's bodies of work that are related to those particular kinds of results in the field. Then other times, and kind of usually, and it depends on whether there's enough naming to fill it in, and it depends on how overloaded or underloaded the term is, you'll have something like simple closed connected curve because those add up. And they have the same usual sense as they do in English. And they have a strict and strong mathematical meaning later that they might implement the same kind of notion as this, what goes into defining what is a simple closed connected curve. Simple like it's non-crossing, connected like it's continuous, closed like it has a beginning and an end point and they're the same. These kinds of things. So anyways, then for this, when we talk about Camille Jordan, then he's got a couple different things associated with him. And so one thing here is about the Jordan measure. And so what's a Jordan measure? It's like, well, it's kind of like Lebesgue measure, but it's a little a little more generous in the sense that makes it a little bit more difficult to make it as strong a rigor. And well, what does that mean? And well, it means in the one-dimensional case that a line can't really be given a measure like a Jordan measure, which is divided into infinitesimally many, infinitely small regions. That a Jordan measure would have to be like this line continuities measure. In fact, that's what it needs to exist as a thing, and how it is. Well, how is that made in mathematics today? Well, what happens in mathematics today is they just defer that until way, way above mathematics, in mathematics, and they call it a complete metrizing ultrafilter. And it models this sort of object and has these sorts of properties. Well, if it models this sort of object and has this sort of properties, isn't it hypocritical to say that it's not itself beneath where it lives also? Well, and it wouldn't be possible to make a model of that and then to see how it's so that it would be breaking things, or that things that should exist would be broken, or that things that should exist cannot exist. This is an example is just one of these kind of things that led to first, before I'm taking this second course in differential analysis, is that I've been studying foundations of continuity for 20 or 30 years. And because what I want is the real theory that's true, of mathematics. That's really all I care about. I don't have any necessary need to be applying any of my mathematics. It's just got to be true and pure. This is not a luxury everybody has. but it's the tack I chose to try to figure it all out. And I figure then when I try to relay it as well to other people, it's the same true for them too. And and that's the requirement and desiderata and requirement of this sort of theory, because it has to be relatable, exchangeable, equi-interpretable. These are the things that make it so possible. Well, all right. When using simple closed Jordan curves consisting of a few straight lines and circular areas, geometrical intuition makes it obvious which is the interior and which is the exterior domain. Here it was framed in terms of that the interior is not infinite. All right, well, I've enjoyed this today. I hope it ends up being an interesting presentation. I wouldn't really depend on it because I plan to make these more sorts just audio-only podcasts. But it will give you an idea of how thick my glasses are, 4 or 5 diopters, and that they hold up pretty well. Here I have this just as a usual nod to frugality in today's world. And I hope this sees you well, you and yours, and have a great day. That the brief rainfall has passed, and it'll be nice and warm out for the rest of this afternoon. And carry on. Good luck.